So now we've done the forward half. We can go ahead and do the backwards pass. And we're not going to be doing it node by node. We're going to actually go ahead and be doing it layer by layer. So the first thing we're going to look at, the first thing we could look at, really, is the partial derivative of L with respect to A4. However, it's probably simpler to take advantage of the fact that we're using a combination of the binary cross entropy along with sigmoid. And we know that if we take the derivative of binary cross entropy, which is our loss function, along with the sigmoid, that we get a very nice formulation, which is just y hat minus y. So we can actually go directly to Z4. And we know that is going to equal y hat minus y. We're going to go ahead and compute layer by layer, because really what backpropagation is a combination of two things. Backpropagation is a combination of the chain rule plus dynamic programming. So what we are doing is, and dynamic programming just says we have problems where we have problems which are composed of smaller subproblems, and we go ahead and use a cache memoization to avoid recomputation. So if we go ahead and compute the gradients for this layer, and then use those to compute the gradients of this layer, and those to compute the gradients for this layer, and those to compute the gradients for this layer, then we are avoiding all the recalculation that we had done when we looked at all the possible paths. So let's look at, now that we've got Z4, let's go ahead, so we have the gradient to here, let's go ahead and compute the gradients to these weights. So we're going to say that the gradients, so those are just going to be equal to A at 3 transpose times the gradient to Z4. Let's see whether this makes sense. So what we know is our gradient to a weight here depends on our gradient all the way up to the Z times the derivative from Z to the weight. Well, we know the derivative of Z to the weight for any particular weight is really just the outgoing A from the previous layer. So it makes sense that we're going to be multiplying by an outgoing A from the previous layer. Let's look at these sizes just to see if this makes sense. So we know W4 is of this form. It's a 2 by 1. So therefore, we know that the gradient is going to be a 2 by 1. So this is going to be a 2 by 1. What do we know the derivative of L with respect to Z4? Well, it's going to be the same form as Z to the 4. So Z to the 4 was a 1 by 1. So this derivative is going to be a 1 by 1. So this derivative is going to be a 1 by 1. Okay. And A3 is of what form? A3 is here a 1 by 2. We need it to be a 2 by 1. So that's why we're going to transpose it. So A3 transpose is going to be a 2 by 1. So we take the 1 by 2 and we transpose it. Kind of makes sense because what we're doing is on the forward pass, we are taking two things and multiplying to get one. And on the backwards pass, we are multiplying this one thing to get 2. Okay, so that's why we have the 2 by 1. So let's just see what this equals, right? This equals A3 transpose. So that's why we stored this all on the way up. So we stored all our intermediate values, our A's and our Z's. So we're going to take A3, which is 2, 3, and we're going to transpose it. So we get 2, 3, and we're going to multiply this by negative 1/2, and that'll equal 1, negative 1, and negative 3/2. So since these gradients are negative, that means that we're going to tend to be increasing the weights here for W4. And for E4, right, if we look at this one, we know that the derivative of z with respect to b is just 1, right? Because z is this weighted sum plus a b at the end. And so the derivative with respect to b is 1. So therefore, b is just equal to the partial derivative with respect to z, which equals 1 by 1, negative 1/2. This computation from a z to the corresponding w and b works at any layer. So once we have calculated the partial derivative of L with respect to z super 3 or z super 2 or z super 1, we know how to calculate the w's and the b's. So now let's look at going from a z in one layer to an a in a previous layer. That is, we've already computed the partial derivative of L with respect to z4. Let's look at the partial derivative of L with respect to a3. Well, again, what can help us is to make sure our matrix dimensions seem correct. So we know what we have is, since a3 is a 1 by 2, we know that this derivative, this gradient, is also going to be a 1 by 2. So we're now going to take the partial derivative to z4. That's going to be this negative 1/2, so this is a 1 by 1. And we know we're going to need to multiply this in order to get this kind of equal to by a 1 by 2. We know the derivative of z with any a here is just the corresponding weight, right? Because we've got this summation of weighted sums. And so for any one arc here, the derivative is the weight. So we're going to actually use this weight matrix, W4. It is a 2 by 1. We need a 1 by 2. That's why we're going to go ahead and use W4 transpose. And again, the idea is kind of we were going from 2 items to 1 item. So our weight matrix was a 2 by 1. Now we're going from 1 to 2. So we need a weight matrix of 1 by 2. And let's calculate this out. So we have our partial derivative here, and then our weight matrix 4, which is 2, 3, transposed. And so this is going to equal negative 1, negative 3/2. So we've seen how to go from a z to a corresponding w, that is the gradient for the w. We've seen how to go from a z to the gradient for a corresponding b. We've seen how to go from a z at one level, at one layer, to an a at a previous layer. The only thing we really need to still do is figure out how to go from one layer to the previous layer. So let's look at that. So we want to compute the derivative, partial derivative of L with respect to z3. So what we're going to do is we're going to take the partial derivative of L with respect to a3. So that'll take us, let's say, from here to here. So we are on the right-hand side, and now we need to go to the left side. So we know they need the partial derivative all the way to the right side. And now we need to multiply the derivative from here. So what we're going to do is, let's look at these sizes again. So z3 is a 1 by 2, just like a3 is a 1 by 2. So z3 is a 1 by 2, a3 is a 1 by 2. And what we're going to do then is go ahead and do a element-wise multiplication. This is called the Hadamard product. And it's basically just element-wise multiplication. So what we're going to do now is multiply by g prime of the input, that is, of z3. Now, in our case, we're looking at the ReLU. Okay, so we basically just now take z3, which we have here, 2, 3, and we take the derivative of that. That is the derivative of ReLU with respect to that. So for ReLU, anything positive, the derivative is 1. So this will just become 1, 1. So let's multiply this out. And this is going to be also a 1 by 2. So we're going to take this derivative here, negative 1, negative 3 halves, do a Hadamard product with the derivative applied to this. So the derivative applied to that is just going to be 1, 1. So this is equal negative 1, negative 3 halves. Okay. So this Hadamard product is just, for instance, in NumPy is just a multiply of two matrices. Two matrices of the same size, same dimensions. So now we have all the building blocks we need. Let's go ahead and write down what our rules are for computing L. Basically, if we can go ahead and say we know how to get from L to the last A, we know how to get from any A to any Z, from any Z to associated W, a Z to a B, and then a Z to a previous A, then we know how to work all the way down. Right? We can just use this recursive. So let's look at that. So, and we will say that we have k layers. So we know that the partial derivative of L with respect to the last layer, what's that going to be equal? Well, that's just going to equal the derivative of the loss applied to the last layer. So that gets us started. And of course, remember this last layer is the same thing as L prime of y hat, right? Because the output of the last layer is in fact y hat. Now we've got that A, we need to get to the associated Z. So this is sort of our base case. This gets us started. And now we say if we've got any A, we can get to the associated Z. And how do we do that? The derivative of the loss with respect to any Z is the derivative of the loss with respect to the associated A, and then use the Hadamard product of that with G super I, that is the G at that layer, take the derivative of that, and apply that to Z at I. Once we've got a Z, we need to be able to calculate the previous layers A and the current layers W and B. So let's do B because that was so simple. So we say that the derivative of the loss with respect to B at any particular layer is equal to the derivative of the loss with respect to Z at that layer. The derivative of the loss with respect to any weight at a given layer is just equal to, as we did over here, so that's the activation at I minus 1, transpose that matrix, and then multiply that by the partial derivative loss with respect to Z. And then finally, our last piece we need is the derivative loss with respect to the, let's say, A at I minus 1. And that's going to equal, right here, the loss with respect to Z at I times the weight matrix at I transpose. So let's just go ahead and finish off these calculations. We got all the way down to Z3. We need to get down to, so we have these weights, these biases, these weights, these biases, these weights, these biases. Let's go ahead and apply these then. We know that the loss with respect to Z3 is equal to the loss with respect to B3. Let's now calculate the gradient of the weights. So at layer 3, we know we want to take the A at 2 transpose. So A at 2 is 0, 2, 1. So we'll transpose that and multiply that by the gradient of Z3. So the gradient of Z3 is negative 3 halves. We know we have a 3 by 1 and a 1 by 2, so we ended up with a 3 by 2. So we have 0, 0, negative 2, negative 3, and negative 1. All right, now let's take the derivative, calculate the derivative loss with respect to A2, and that equals the loss with respect to Z3, which is negative 3 halves, and then multiply that by the weight matrix transposed. This would have been a good idea if I hadn't actually erased the weight matrix, huh? So I happen to have the weight matrix written down, and so that is, let's see, transposed is 1, 2. So sorry, we're going to need, yes, 1, 2, 1, 1, 1, 2. And that is a 1 by 2 by a 2 by 3. So we're going to end up with a 1 by 3. Negative 1 plus negative 3 is negative 5. Negative 1 plus negative 3 halves is negative 5 halves. Negative 1 plus negative 3 is negative 5. All right, good news. We're not actually going to need any of these anymore, right? We've already calculated the derivative of Z3 with respect to A4 and Z4 and W4 and B4 and Z3 and B3. And so let's just go ahead and erase this so we have some room more to work. Loss with respect to Z2, and that's going to just equal, so it's a loss with respect to A2, which is negative 5 halves, negative 5. Hadamard producted with the derivative of Z at I. So the derivative of Z at I, that's of Z at 2, right? We have a negative 5, 2, 1. The derivative of that, well, the negative 5, we know that the value is 0, so we have a slope of 0 when we're negative and a slope of 1 when we're positive. So this is going to be 0, 1, 1. And that equals 0, negative 5 halves, negative 5. Now we can go ahead and calculate, and this we know also equals the partial derivative of L with respect to B at 2. Okay, now the partial derivative of L with respect to W at 2. W says we take the previous A matrix, so that's A at 1, which was a 1, and we transpose it. I know how to do that. So that's just 1. And we multiply by, we're here, and we multiply by the loss of Z. So that's going to be, so that's just going to equal 0, negative 5 halves, negative 5. So now we're down to layer 2. We can move on to layer 1, which, thank goodness, is our last layer. So we'll need to do our A at 1. We see A at 1 is the derivative with respect to Z at the previous layer, so that's 0, negative 5 halves, negative 5 times that weight matrix transposed. I happen to have, let's say, weight matrix 1 was 4, negative 2. So I pulled that back out of the vault. So I happen to have the other two matrices. So W1 was 4, negative 2, and W2 is negative 5, 2, 1. So this transposed is, which equals 0 plus negative 5 plus negative 5. Z from A just equals z from A equals the derivative with respect to A, the Hadamard product of g prime of z at 1. So z at 1 was 1. Its derivative, since this value is positive, is 1. So this just equals negative 10. This also equals the partial derivative of L with respect to B at 1. And what else do we need to calculate? Well, there's just one more thing we need to calculate, and that is what's the derivative of L with respect to the weight matrix at 1. No reason to calculate the derivative with respect to A0 because x is we're not ever going to be changing x, right? We don't care about that. So all we care about is our final weight matrix. So this is going to be equal for a weight matrix. So we take the previous A's and transpose it. So that's A at 0 transposed. So that's going to be 3, 5 times partial derivative of L with respect to z, which equals negative 10. So that equals, so a 2 by 1 by 1 by 1 is a 2 by 1, which equals negative 30, negative 50. So it sounds like these weights are going to be going up a lot, right? We've got a huge gradient here. So that is a long example of actually doing backpropagation. It is relatively similar to doing the forward propagation. We're just using slightly different rules. These are the rules that we use.